In this very moment, as you sit reading these words, some of the atoms in your body might be instantaneously connected to particles orbiting a distant star, sharing information across the vast emptiness of space, faster than light itself could ever travel. We've always thought of ourselves as isolated beings on a lonely planet, separated from the cosmos by incomprehensible distances and empty void. Our atoms seem private, contained within the boundaries of our skin, disconnected from the universe beyond. And yet, the deepest secrets of quantum mechanics suggest something far more profound and mysterious. What if the very particles that make up your body are still quantum entangled with matter scattered across the galaxy? What if the universe isn't a collection of separate objects, but rather a single, interconnected quantum system where every particle remembers its cosmic relationships? Join me as we dive into the most mind-bending theory in modern physics, where Einstein's deepest fears about reality have proven true, where distance becomes meaningless, and where the atoms forged in ancient stellar cores might still be whispering to each other across the cosmos. Before we embark on this quantum journey together, let me know where in the world you're watching from and what time of day it is where you are. Drop your location and local time in the comments below. I love seeing how this cosmic story reaches people across our planet. Picture Albert Einstein in 1935, sitting in his Princeton office, deeply troubled by the implications of his own work. The man who had revolutionized our understanding of space, time, and gravity was now confronting something that made him profoundly uncomfortable. The emerging field of quantum mechanics was suggesting that particles could be mysteriously connected across any distance, instantly affecting each other in ways that seemed to mock the very foundation of physics. Einstein famously called this phenomenon "spookhafte Fernwirkung," spooky action at a distance. It wasn't just scientific skepticism that drove his criticism. It was a visceral rejection of what quantum entanglement implied about the nature of reality itself. For Einstein, the universe was deterministic, local, and rational. Every effect had a cause, and that cause had to travel through space to reach its target. Nothing could influence something else instantaneously across vast distances. It violated everything he believed about how the cosmos operated. The source of Einstein's discomfort was a thought experiment he developed with colleagues Boris Podolsky and Nathan Rosen, now known as the EPR paradox. They imagined two particles that interact and then fly apart to opposite ends of the universe. According to quantum mechanics, these particles would remain connected in such a way that measuring one would instantly determine the state of the other, regardless of the distance between them. To Einstein, this was absurd. God does not play dice with the universe, Einstein declared. But quantum entanglement suggested something even more troubling, that God might be a cosmic magician, making particles communicate through some impossible quantum telepathy. Einstein couldn't accept that measuring a particle on Earth could instantly affect its partner near Alpha Centauri, 4 light-years away. Such instantaneous influence would require information to travel faster than light, violating his own theory of special relativity. What made this even more maddening for Einstein was that quantum mechanics worked. Its predictions were astoundingly accurate, describing atomic behavior with unprecedented precision. Yet the theory seemed to describe a universe that was fundamentally uncertain, where particles existed in multiple states simultaneously until observed, and where distant objects could be mysteriously correlated in ways that defied common sense. Einstein spent the last decades of his life searching for what he called a theory of everything, a unified field theory that would restore order to physics and eliminate the need for quantum uncertainty. He was convinced that quantum mechanics was incomplete, that there had to be hidden variables governing particle behavior that scientists simply hadn't discovered yet. In his view, particles weren't truly random or mysteriously connected. They were following predetermined paths determined by forces we couldn't yet detect. The great physicist believed that once these hidden variables were found, the apparent spookiness of quantum entanglement would dissolve. The particles weren't really communicating faster than light. They were simply following a cosmic script written at the moment of their creation. Like two coins that had been programmed to always land on opposite sides, entangled particles would only appear mysteriously connected because we didn't understand the hidden mechanism governing their behavior. But Einstein's intuition about reality would soon be put to the ultimate test, and the universe would reveal itself to be even stranger than he feared. Einstein's quest to find hidden variables wasn't just academic stubbornness, it represented a fundamental clash between two visions of reality. On one side stood quantum mechanics, describing a universe of uncertainty and mysterious connections. On the other stood Einstein's classical worldview, where everything had a definite state and local causes produced local effects. The hidden variables theory was elegant in its simplicity. Imagine two entangled particles as cosmic twins, created with complementary properties already determined, like two halves of a secret code. When these particles separated, they would carry their predetermined instructions across the universe. Measuring one particle wouldn't magically affect the other. It would simply reveal the predetermined plan that both particles had been following all along. This interpretation preserved Einstein's cherished principle of locality, the idea that objects are only influenced by their immediate surroundings. A particle near Earth couldn't instantly affect its partner near a distant star because no information needed to travel between them. The correlation was already built into their quantum DNA from the moment of their creation. For decades, Einstein's hidden variables theory seemed like a reasonable alternative to quantum mechanics' more exotic claims. After all, how could anyone prove that particles were truly communicating instantaneously rather than following hidden instructions? The debate seemed destined to remain forever philosophical, a matter of interpretation rather than experimental fact. Einstein continued his search throughout the 1940s and early 1950s, convinced that a deeper theory would eventually emerge to explain quantum phenomena without resorting to spooky action. He imagined a universe where every particle carried invisible information about its quantum state, like a secret passport that determined its behavior throughout its cosmic journey. The hidden variables approach suggested that our atoms might indeed be connected to distant stars, but not through any mysterious quantum communication. Instead, they would be connected through shared history particles that were once together in stellar cores, would carry identical hidden information about their quantum states, creating the illusion of ongoing communication across galactic distances. This worldview was comforting because it preserved human intuition about cause and effect while still explaining quantum correlations. It suggested that the universe, despite its quantum weirdness, still operated according to comprehensible rules. Particles weren't engaging in supernatural communication. They were simply following an incredibly complex but deterministic cosmic choreography. But nature, as we would soon discover, had no intention of conforming to human intuition about how reality should work. The universe was preparing to reveal that Einstein's worst fears about quantum mechanics were not only justified, they were understatements of just how strange reality truly is. In 1964, a quiet physicist working at CERN named John Stuart Bell accomplished something that had seemed impossible for nearly 3 decades. He found a way to test whether Einstein was right about hidden variables, settling once and for all whether quantum entanglement was real or just an illusion created by our incomplete understanding of physics. Bell's approach was brilliantly simple, yet mathematically profound. He realized that if Einstein's hidden variables existed, they would create mathematical constraints on how correlated two entangled particles could be. Think of it this way. If particles were following predetermined instructions rather than communicating instantly, there would be limits to how perfectly coordinated their behavior could appear to distant observers. Bell constructed what became known as Bell's inequality, a mathematical boundary that local hidden variable theories could never cross. If particles were carrying secret information about their states, their correlations would be strong, but limited by the constraint that they couldn't share new information faster than light. However, if quantum mechanics was correct and particles were truly entangled, their correlations could violate Bell's inequality, showing correlations stronger than any local hidden variable theory could explain. The theorem was revolutionary because it transformed a philosophical debate into a testable scientific hypothesis. For the first time, physicists had a way to determine whether the universe was fundamentally local and deterministic, as Einstein believed, or non-local and mysterious, as quantum mechanics suggested. Bell's inequality can be understood through a simple analogy. Imagine 3 boxes, each containing either a red or blue ball. In Einstein's world of hidden variables, the colors are predetermined fixed from the moment the boxes are created. If you randomly choose two boxes and open them, there are limits to how often you'll find matching or contrasting colors based on the initial probability distribution. But quantum mechanics predicts something different. It suggests that the balls don't have definite colors until the boxes are opened, and more incredibly, that opening one box can instantly influence the color of balls in distant boxes. This quantum prediction violates Bell's inequality, showing correlations that are impossible if the colors were predetermined. Bell's theorem revealed that any theory explaining quantum phenomena must be either non-local or non-realistic. Non-locality means that particles can influence each other instantaneously across any distance. Non-realism means that particles don't have definite properties until they're measured. Either option violated fundamental assumptions about reality that had guided physics for centuries. The implications were staggering. Bell had proven that if quantum mechanics was correct, then either faster-than-light influences exist in nature, or the very concept of objective reality, the idea that objects have definite properties independent of observation, must be abandoned. Einstein's hope for a local, realistic, deterministic universe was mathematically impossible if quantum mechanics accurately described nature. Bell himself was initially skeptical of quantum mechanics, hoping his theorem would expose its flaws and vindicate Einstein's position. Instead, he had created the framework for proving that the universe was far stranger than anyone had imagined. The theorem suggested that the atoms in our bodies might indeed be connected to distant cosmic matter through non-local quantum correlations that transcend space and time. What made Bell's work even more remarkable was its testability. Unlike purely philosophical arguments about the nature of reality, Bell's inequality could be measured in laboratory experiments. Scientists could create entangled particle pairs, separate them by large distances, and measure their correlations to see whether nature violated Bell's inequality. The stage was set for one of the most important experimental tests in the history of physics. Would nature conform to Einstein's local realism, staying safely within Bell's inequality? Or would the universe reveal itself to be fundamentally non-local, with particles maintaining impossible connections across cosmic distances? Bell had given physicists the tools to peer behind the quantum veil and discover whether our atoms might truly be connected to distant stars through mysterious quantum threads that bind the universe together in ways that transcend our everyday understanding of space and time. The moment of truth came in 1981, in a laboratory in Paris where French physicist Alain Aspect performed what many consider the most important experiment in quantum physics history. Armed with Bell's mathematical framework, Aspect set out to determine once and for all whether Einstein or quantum mechanics was correct about the nature of reality. Aspect's experimental setup was elegantly simple, yet technically demanding. He created pairs of entangled photon particles of light that were quantum mechanically connected and sent them speeding in opposite directions toward detectors located several meters apart. The key was to measure the polarization of these photons along different angles and compare the correlations between their measurements. If Einstein was right about hidden variables, the correlations would respect Bell's inequality, showing strong but limited coordination between the photon pairs. If quantum mechanics was correct, the correlations would violate Bell's inequality, demonstrating impossible coordination that could only be explained by non-local quantum entanglement. The results were unambiguous and revolutionary. Nature violated Bell's inequality. The entangled photons showed correlations that were mathematically impossible if they were following predetermined hidden variables. Quantum mechanics wasn't just correct, it was describing a universe far more interconnected and mysterious than Einstein had ever feared. Aspect's experiment revealed that when one photon was measured and found to have vertical polarization, its entangled partner instantly knew to exhibit horizontal polarization, even though the particles were separated by distances that light couldn't cross in the time between measurements. This wasn't coincidence or predetermined coordination, it was genuine instantaneous correlation across space. The implications rippled through the physics community like a quantum earthquake. Einstein's local realism was dead, killed by the very particles he had hoped would vindicate his worldview. The universe was fundamentally non-local, meaning that particles could influence each other instantly across any distance, or non-realistic, meaning that particles didn't have definite properties until measured. But Aspect's work was just the beginning. In the decades that followed, physicists around the world performed increasingly sophisticated tests of Bell's inequality, closing potential loopholes and extending the distance between entangled particles. Experiments demonstrated entanglement across continents, from ground stations to satellites, and even between particles that had never directly interacted. Each experiment confirmed the same startling conclusion: quantum entanglement is real, and the universe is non-local. Particles separated by thousands of kilometers maintain correlations that violate our classical understanding of cause and effect. Information isn't traveling between these particles faster than light. Instead, they exist in a shared quantum state that transcends our normal concepts of space and separation. These experimental confirmations transformed our understanding of cosmic connections. If particles created in the same quantum event could maintain their entanglement across laboratory distances, what about particles created in stellar cores billions of years ago? Could the atoms forged in ancient supernovae still be quantum entangled with matter scattered across the galaxy? The experiments also revealed the fragility of entanglement. Quantum correlations are easily disrupted by interaction with the environmental process called decoherence. This suggested that while cosmic entanglement might theoretically persist across vast distances, maintaining these connections in the noisy, chaotic environment of space would be extremely challenging. Yet the fundamental principle remained: the universe operates on non-local quantum mechanics. The atoms in our bodies were created in stellar furnaces, where particles were intimately connected at the quantum level. Some of these connections might have survived the violent processes of stellar death, supernova explosions, and cosmic evolution, creating invisible threads linking earthbound matter to distant stellar remnants. Aspects experiment and its successors didn't just prove quantum mechanics correct. They revealed that we live in a universe where the impossible is routine, where particles mock the constraints of space and time, and where the very atoms that compose our bodies might be engaged in an eternal quantum conversation with matter scattered across the cosmos. To truly understand how your atoms might be connected to distant stars, we need to grasp what quantum entanglement actually looks like at the particle level. Imagine two dancers who have practiced together for so long that they move in perfect synchronization, even when separated by vast distances and unable to see or hear each other. When two particles become entangled, they lose their individual quantum identities and merge into a single, shared quantum system. It's not that they're communicating with each other, they've become different parts of the same quantum entity. Think of entangled particles as two hands of the same cosmic being, where moving one hand instantly affects the other, not because a signal travels between them, but because they're part of the same unified system. This unity persists regardless of distance. Whether the particles are separated by millimeters or light years, they remain part of the same quantum whole. When you measure one particle and find it spinning clockwise, its entangled partner will instantly be found spinning counterclockwise, not because your measurement sent information across space, but because the two-particle system has a definite total angular momentum that must be conserved. The mathematics of entanglement reveals something profound about the nature of reality. Entangled particles exist in what physicists call a superpositioner quantum state, where they're simultaneously in all possible configurations until measured. A pair of entangled particles might be in a state where both are spinning up and both are spinning down, all at the same time, until the moment someone observes one of them. This isn't just theoretical abstraction. Modern experiments can create entangled particles and verify their shared quantum state through precise measurements. Scientists can prepare photons, electrons, or even larger objects in entangled states, and confirm that measuring one instantly determines the state of its partner, regardless of the distance between them. The process of creating entanglement often involves bringing particles into close interaction and then separating them while preserving their shared quantum state. In nature, this happens constantly. When atoms form and break apart, when particles collide in cosmic ray showers, when matter is compressed in stellar cores, countless opportunities arise for particles to become entangled and then spread across the universe. Consider the atoms in your body, forged in the nuclear furnaces of ancient stars. As these stellar cores collapsed and exploded, particles that had been intimately connected at the quantum level were scattered across the galaxy. Some became part of the gas clouds that eventually condensed into our solar system, while others were flung toward distant star systems, carrying their quantum connections across the cosmic void. The key insight is that entanglement doesn't require ongoing communication between particles. Once created, the quantum correlation exists as a fundamental property of the shared system. The particles don't need to send signals to each other to coordinate their behavior. They're already part of the same quantum reality, like two sides of a single coin that always show heads and tails simultaneously. This understanding transforms how we think about cosmic connections. Your atoms aren't sending messages to distant stars. They might literally be part of the same quantum system as particles orbiting those stars, connected through invisible quantum threads that were woven in the hearts of dying suns billions of years ago. Quantum entanglement forces us to confront the possibility that space and time, the very framework through which we understand reality, might be emergent properties of something deeper and more fundamental. When entangled particles maintain their correlations instantaneously across cosmic distances, they're revealing that the universe operates on principles that transcend our everyday experience of separation and sequential time. Einstein's special relativity taught us that nothing can travel faster than light, yet entangled particles seem to coordinate their behavior instantaneously, regardless of the distance between them. This isn't a violation of relativity information, or energy travels between the particles. Instead, it suggests that the particles exist in a quantum realm where distance is irrelevant, where the concepts of here and there lose their meaning. Think of it this way. If two particles are truly entangled, they don't exist at separate locations in any meaningful sense. They exist in a quantum superposition that encompasses both positions simultaneously. When we measure one particle at location A, we're not causing something to happen at location B. We're collapsing a single quantum wave function that already included both locations. The measurement reveals the state of the entire system, not just the local particle. This perspective revolutionizes our understanding of cosmic connections. The atoms in your body and particles orbiting distant stars might not be connected across space. They might exist in the same quantum space, a realm where galactic distances are as meaningless as the distinction between left and right hands on a single body. Recent theoretical work in quantum gravity suggests that space itself might emerge from quantum entanglement. In this view, the fabric of space-time is woven from quantum correlations between particles, with entanglement creating the geometric relationships we experience as distance and dimension. If this theory is correct, then entangled particles aren't separated by space. They're helping to create space through their quantum connections. The implications for time are equally profound. Quantum entanglement appears to be instantaneous, but instantaneous assumes a universal concept of simultaneity that Einstein showed doesn't exist. Different observers moving at different speeds will disagree about when events happen, yet entangled particles maintain their correlations regardless of the observer's reference frame. This suggests that entanglement operates in a temporal realm beyond our normal experience of past, present, and future. The quantum connections between particles might exist in what physicists call block time, an eternal, four-dimensional structure where all moments exist simultaneously. From this perspective, particles entangled billions of years ago in stellar cores remain connected in an eternal now that transcends the flow of cosmic time. Modern experiments have begun to explore these temporal aspects of entanglement. Scientists have created delayed choice experiments, where the decision about how to measure one particle is made after its entangled partner has already been detected. Remarkably, the later decision seems to retroactively determine the state of the earlier measurement, suggesting that quantum correlations can reach backward through time as easily as they span across space. These discoveries point toward a universe where cause and effect, the fundamental organizing principles of classical physics, become fluid and ambiguous. If particles in your body are entangled with matter near distant stars, their quantum correlations might exist in a timeless realm where the stellar nuclear fusion that created them, their journey through space, and their incorporation into biological molecules are all equally present and equally real. The philosopher-physicist David Bohm proposed that our normal experience of separate objects moving through space and time is like watching shadows on a cave walla, limited projection of a deeper, more unified reality. In Bohm's view, entangled particles reveal glimpses of this underlying, implicate order, where all things are interconnected in a seamless quantum wholeness. If Bohm was right, then asking whether your atoms are connected to distant stars is like asking whether your reflection is connected to your body. The connection isn't something that crosses space and time. It's a fundamental unity that exists beneath the apparent separations we observe in the everyday world. This quantum view of reality suggests that the universe might be far more intimate and interconnected than we ever imagined, where every particle carries within it the story of cosmic evolution, and where the boundaries between self and cosmos dissolve into a single, eternal quantum dance. Perhaps the most mind-bending aspect of quantum entanglement is the role that observation and measurement play in determining reality itself. When we ask whether your atoms are connected to distant stars, we're confronting the possibility that the very act of asking, of measuring and observing helps to create the answer. In the classical world we're familiar with, measurements simply reveal pre-existing properties. When you check the temperature outside, you're discovering a condition that existed whether you measured it or not. But quantum mechanics suggests something far more radical, that particles don't have definite properties until they're measured, and that the act of measurement doesn't just reveal reality, it participates in creating it. Consider two entangled particles, one in a laboratory on Earth and its partner somewhere in the vicinity of Alpha Centauri. According to quantum mechanics, before any measurement is made, both particles exist in a superposition of all possible states. The earthbound particle is simultaneously spinning up and down, left and right, in all possible orientations at once. Its distant partner is similarly existing in a ghostly superposition of complementary states. The measurement paradox emerges when we observe one of these particles. The instant we measure the Earth particle's spin and find it rotating clockwise, its distant partner instantly becomes locked into a counterclockwise rotation, even though it's 4 light-years away and no signal could have traveled between them. But here's the crucial question. Did our measurement on Earth create the definite states of both particles, or did it simply reveal states that already existed? Quantum mechanics suggests the former, that measurement plays an active role in crystallizing reality from a sea of quantum possibilities. This interpretation implies that consciousness, or at least measurement apparatus, serves as the bridge between the quantum realm of infinite potential and the classical world of definite outcomes. When you measure a particle's property, you're not just learning about reality, you're participating in its creation. The implications for cosmic entanglement are staggering. If particles in your body are entangled with matter near distant stars, then every quantum measurement in your biological processes, every photon absorbed by your retina, every electron transferred in cellular metabolism, every quantum event in your neural networks might be instantly affecting quantum states throughout the galaxy. Your consciousness, which depends on countless quantum processes in your brain, might be part of a vast measurement network that helps determine the quantum states of particles across cosmic distances. Every thought, every sensory experience, every moment of awareness might be contributing to the ongoing creation of reality on a galactic scale. This perspective transforms the ancient philosophical question of whether the tree falling in an empty forest makes a sound. In quantum terms, the tree might not even have a definite position, momentum, or existence until something observes it. And if that tree contains atoms that are entangled with particles scattered throughout the universe, then its collapse might instantly affect quantum states in distant galaxies. Modern interpretations of quantum mechanics have struggled with this measurement problem. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, embraces the active role of measurement, but remains vague about what constitutes a measurement and why classical devices seem to have definite properties, while quantum particles exist in superposition. The many worlds interpretation offers an alternative view. Every possible measurement outcome occurs, but in separate parallel universes. In this framework, when you measure an entangled particle, you're not creating its state, you're determining which branch of the multiverse you experience. Your consciousness splits along with reality, with different versions of you experiencing different measurement outcomes in parallel cosmic branches. Hugh Everett III, who developed the many worlds interpretation, suggested that entanglement creates branching points across the universe. When particles in your body, entangled with distant stellar matter, undergo quantum measurements, reality splits into multiple branches. In some branches, The measurements yield one set of correlated outcomes. In others, different correlations manifest. Your consciousness experiences just one branch, but infinite versions of you exist across the quantum multiverse. Recent developments in quantum information theory have added another layer to the measurement paradox. Scientists have discovered that information itself might be the fundamental substance of reality, with matter and energy as emergent properties of informational relationships. From this perspective, entangled particles don't just share correlations, they share information in ways that transcend space and time. If consciousness is also fundamentally informational, as many neuroscientists and philosophers suspect, then your awareness might be directly participating in the cosmic information network that connects entangled particles across the universe. Your thoughts and perceptions might be part of an ongoing information exchange with stellar matter throughout the galaxy. The measurement paradox also raises questions about the nature of time and causality. If measurement outcomes can be delayed or even reversed in certain quantum experiments, then the definite states of particles might exist in a timeless realm where past, present, and future measurements all contribute simultaneously to the quantum state. This suggests that your current measurements of quantum systems might be retroactively determining the states of particles that were entangled billions of years ago in stellar cores. Conversely, measurements being made by hypothetical alien civilizations around distant stars might be influencing quantum states in your body right now, creating a cosmic web of mutual quantum influence that transcends normal concepts of cause and effect. The measurement paradox ultimately suggests that consciousness and cosmos are not separate entities but aspects of a single, interconnected quantum reality where observation, entanglement, and the creation of definite states from infinite possibilities are ongoing collaborative processes spanning the entire universe. To understand how your atoms might be connected to distant stars, we must journey back to the beginning of everything, the Big Bang when the entire observable universe existed in a state of perfect quantum entanglement. In those first infinitesimal moments, when all of reality was compressed into a space smaller than a proton, every particle that would ever exist was intimately connected in a single, unified quantum system. Imagine the early universe as the ultimate quantum computer, with every particle serving as a quantum bit entangled with every other particle. Temperature, pressure, and energy were so extreme that matter existed in exotic phases we can barely comprehend today. Quarks swam freely in a primordial soup. Electrons hadn't yet been captured by atomic nuclei, and the four fundamental forces of nature were unified into a single cosmic force. In this environment, quantum entanglement wasn't just possible, it was inevitable and universal. As particles collided, combined, and separated in the cosmic maelstrom, they created an intricate web of quantum correlations that connected every piece of matter to every other piece. The universe was born as a single, entangled quantum entity. As the cosmos expanded and cooled, this initial entanglement began to evolve. Some quantum connections were preserved as particles separated across growing distances. Others were disrupted by decoherence, the process by which quantum systems lose their coherence due to interaction with their environment. But the fundamental principle remained. Every particle in the universe shared a common quantum origin and potentially retained vestiges of its primordial connections. The formation of the first atomic nuclei during Big Bang nucleosynthesis created new opportunities for entanglement. As protons and neutrons combined to form hydrogen and helium nuclei, particles that had been separate became bound in quantum systems where their properties were correlated. When these nuclei later captured electrons to form neutral atoms, even more complex entangled states emerged. But the most significant moment for cosmic entanglement came with the birth of the first stars. When gravity began pulling together vast clouds of primordial gas, it concentrated not just matter, but also the quantum correlations that had been diluted by cosmic expansion. As stellar cores reached the temperatures and pressures necessary for nuclear fusion, particles were forced into intimate contact, creating new entangled systems on a massive scale. Inside stellar cores, the process of nuclear fusion constantly creates and destroys entangled particle pairs. When hydrogen nuclei fuse to form helium, the resulting particles carry quantum information about their creation process. As heavier elements form through successive fusion reactions, the quantum correlations become increasingly complex, creating elaborate networks of entanglement within each star. The death of massive stars through supernova explosions represents a crucial moment in cosmic entanglement history. These violent events scatter stellar matter across interstellar space, while potentially preserving some of the quantum correlations created during billions of years of nuclear fusion. Particles that were once entangled in stellar cores become separated by light years, yet they might retain their quantum connections, like cosmic memory of their stellar origin. Some of this stellar debris eventually found its way into the molecular cloud that formed our solar system. The atoms in your body, carbon, nitrogen, oxygen, iron, and dozens of other elements were forged in stellar cores where they existed in quantum entangled states with countless other particles. When these atoms were scattered by supernovae and later incorporated into planets and life, they might have carried their quantum correlations with them. Modern cosmology has found evidence for these primordial quantum correlations in the cosmic microwave background, the afterglow of the Big Bang that still permeates space. Tiny fluctuations in this ancient light reveal quantum mechanical patterns that were stretched across the universe during cosmic inflation. These patterns suggest that quantum entanglement on enormous scales was indeed present in the early universe and might persist today in modified forms. The implications are profound. The universe might be permeated by a background of quantum entanglement that connects matter across cosmic distances. Your atoms, forged in stellar cores billions of years ago, might still be quantum correlated with stellar matter scattered throughout the galaxy. The calcium in your bones, the iron in your blood, the carbon in your DNA, of these elements carry within their quantum structure the memory of their stellar birth and their potential connections to distant cosmic matter. Recent theoretical work in cosmology suggests that this universal entanglement network might be observable through subtle correlations in the properties of matter across vast distances. If confirmed, these observations would reveal that we live in a universe where quantum mechanical connections truly span from the smallest scales to the largest, binding all matter together in an invisible web of correlation that has persisted since the dawn of time. Hidden within the oldest light in the universe lies evidence of cosmic quantum entanglement that has survived for nearly 14 billion years. The cosmic microwave background radiation, the afterglow of the Big Bang carries within its subtle patterns the quantum fossil record of universal entanglement from the earliest moments of cosmic history. When astronomers study this ancient light with extraordinary precision, they discover something remarkable. The tiny temperature fluctuations across the sky show patterns that can only be explained by quantum mechanical processes operating on cosmic scales. These aren't random variations but quantum signatures that reveal how entangled particles in the early universe evolved as space itself expanded. The patterns emerge from a process called cosmic inflation, when the universe underwent explosive expansion in its first fraction of a second. During inflation, quantum fluctuations that began on subatomic scales were stretched to cosmic proportions, creating the seeds for all the structure we see in the universe today. But these fluctuations weren't independent. They were quantum entangled across regions of space that are now separated by billions of light years. Think of it like stretching a quantum rubber sheet embedded with entangled particles. As the sheet expands, the particles separate, but their quantum correlations remain intact, now spanning distances that dwarf entire galactic clusters. The cosmic microwave background captures a snapshot of these correlations, frozen in time like quantum fossils preserved in ancient light. Modern satellites like Planck and WMAP have mapped these quantum patterns with unprecedented accuracy, revealing subtle correlations between regions of space that have never been in causal contact since inflation ended. These non-Gaussian correlations in the cosmic microwave background provide direct observational evidence that quantum entanglement operates on the largest scales in nature. What makes this discovery particularly profound is that it connects quantum mechanics typically studied in laboratories with individual particellostocosmology, which deals with the universe as a whole. The same quantum principles that govern entangled photons in modern experiments were operating on cosmic scales in the early universe, creating correlations that persist across space and time. These cosmic quantum fossils also preserve information about the particles that existed in the early universe. As the cosmos cooled and evolved, some primordial particles decayed or transformed into the matter we observe today. But their quantum correlations, impressed upon the cosmic microwave background, provide a record of their existence and their entangled relationships. For the atoms in your body, this quantum fossil record tells a remarkable story. The elements that compose you were created much later in stellar cores, but they formed within a universe already permeated by quantum correlations from the Big Bang. As gravity pulled together the molecular clouds that eventually formed our solar system, it wasn't just gathering ordinary matter, it was collecting material that existed within this background of universal quantum entanglement. Some researchers propose that this primordial entanglement network might still influence the quantum behavior of matter today. While most quantum correlations from the Big Bang have been disrupted by billions of years of cosmic evolution, the most stable entangled states might have survived, creating a subtle but persistent quantum background that connects matter across cosmic distances. The study of cosmic quantum fossils also reveals how information has propagated through the universe since the beginning of time. Quantum correlations represent a form of information, storage, and transmission that transcends normal concepts of space and time. The patterns we observe in the cosmic microwave background are information from the earliest moments of cosmic history, preserved in quantum correlations and transmitted across billions of years and light years. This quantum fossil record suggests that the universe has been continuously generating and preserving quantum information since its birth. Every stellar fusion reaction, every supernova explosion, every planetary formation has added new layers to this cosmic information network. Your atoms, born in stellar cores and scattered across the galaxy, carry within their quantum structure both the information of their stellar origin and their potential connections to the broader quantum network that permeates the cosmos. The cosmic microwave background thus serves as both a window into the quantum past and a map of potential quantum connections that might still link matter across the universe, including the very atoms that compose your body. Carl Sagan's famous declaration that "we are made of star stuff" takes on profound new meaning when viewed through the lens of quantum entanglement. The atoms composing your body weren't just created in stellar cores, they were forged in environments where quantum entanglement operated on scales we're only beginning to understand, potentially creating connections that persist across the galaxy today. Every carbon atom in your DNA, every oxygen atom in the water that flows through your cells, every iron atom in the hemoglobin that carries oxygen through your bloodstream, all of these elements were born in the nuclear furnaces at the hearts of massive stars. But their creation wasn't a simple assembly line process. It was a quantum mechanical dance of extraordinary complexity, where particles were continuously created, destroyed, and entangled in ways that might have forged lasting connections across cosmic distances. Inside stellar cores, temperatures reach hundreds of millions of degrees, and pressures exceed billions of times Earth's atmospheric pressure. Under these extreme conditions, atomic nuclei overcome their natural electromagnetic repulsion and fuse together, releasing energy and creating heavier elements. But this process isn't just about individual particles colliding. It's about quantum systems interacting, merging, and separating in ways that preserve quantum information about their encounters. When 4 hydrogen nuclei fuse to create 1 helium nucleus in the proton-proton chain reaction, the process involves multiple quantum mechanical steps where particles exist in superposition states and become entangled with one another. The resulting helium nucleus carries quantum information about all 4 original hydrogen nuclei, creating a complex quantum state that connects the new particle to its constituent parts. As stellar evolution progresses and heavier elements form through successive fusion reactions, these quantum connections become increasingly intricate. Carbon forms through the triple alpha process, where 3 helium nuclei must simultaneously overcome quantum barriers to create a stable carbon nucleus. Oxygen forms when carbon captures another helium nucleus. Silicon, sulfur, argon, and iron form through increasingly complex fusion networks, where dozens of particles contribute to each new nucleus. At each step, quantum entanglement plays a crucial role. The wave functions of the interacting particles overlap, creating superposition states where the individual identity of each particle becomes subsumed into the quantum state of the larger system. When these reactions produce the final heavy elements, the resulting nuclei carry within their quantum structure the memory of every particle that contributed to their formation. But the quantum story becomes even more extraordinary when we consider the timescales involved. Massive stars live for millions of years, continuously fusing lighter elements into heavier ones. During this time, particles within the stellar core undergo countless interactions, creating, breaking, and reforming quantum entangled states. Some entanglement relationships are short-lived, lasting only microseconds before decoherence destroys them. Others might persist for much longer periods, creating stable quantum correlations between particles that will eventually be scattered across the galaxy. The process of stellar nucleosynthesis also creates what physicists call correlation networks, complex webs of quantum entanglement connecting particles throughout the stellar core. When carbon atoms form through the triple alpha process, they might retain quantum correlations not just with their constituent helium nuclei, but with other carbon atoms formed through similar processes. These correlation networks could, in principle, connect all the heavy elements created during a star's lifetime into a vast quantum system. The death of massive stars through supernova explosions represents the most dramatic moment in this cosmic quantum story. When a star exhausts its nuclear fuel, its core collapses in milliseconds, releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. This catastrophic event doesn't just scatter stellar matter across interstellar space, it does so while potentially preserving some of the quantum correlations that formed during millions of years of stellar nucleosynthesis. The shock waves from supernova explosions create conditions even more extreme than stellar cores, with temperatures reaching billions of degrees and pressures that compress matter beyond nuclear density. Under these conditions, new quantum entangled states might form even as others are destroyed. The elements scattered by the explosion, including those that would eventually become part of your body, carry with them the quantum history of their stellar origin. Some of these stellar remnants eventually found their way into the molecular cloud that collapsed to form our solar system 4.6 billion years ago. As gravity pulled together dust and gas from multiple stellar sources, it wasn't just collecting raw materials for planets, it was gathering particles that might have retained quantum correlations from their various stellar origins. The iron in your blood, for example, was likely created in a massive star that exploded billions of years ago, possibly in a different region of the galaxy. During its formation, this iron nucleus became quantumly entangled with other particles in the stellar core. When the star exploded, some of those other particles might have been scattered toward completely different parts of the galaxy, while your iron atoms eventually found their way to Earth. If quantum correlations can survive the violence of stellar explosions and the long journey through interstellar space, then the atoms in your body might still be entangled with stellar matter scattered across thousands of light years. Your cellular metabolism, which depends on these stellar-born atoms, might be participating in quantum processes that connect you to the cosmic web of matter distributed throughout the galaxy. Recent research in astrobiology has begun to explore whether quantum effects in biological systems might preserve or even amplify these cosmic quantum connections. Some scientists propose that the quantum coherence observed in photosynthesis, enzyme catalysis, and possibly even consciousness might create biological amplifiers for subtle quantum correlations that link terrestrial life to its cosmic origins. This perspective transforms our understanding of what it means to be human. We're not just made of star stuff, we might be active participants in a galactic quantum network that has been evolving since the first stars ignited. Every breath you take, every heartbeat, every thought might be part of an ongoing quantum conversation with the cosmos that began in stellar cores billions of years ago and continues across the vast distances of interstellar space. The violent death of massive stars through supernova explosions presents one of the most intriguing challenges to cosmic quantum entanglement. Can quantum correlations survive the most energetic events in the universe? When a star that has harbored entangled particles for millions of years suddenly releases the energy equivalent of billions of suns, what happens to the delicate quantum connections that formed during stellar nucleosynthesis? Supernovae are cosmic cauldrons, where the normal rules of physics are pushed to their absolute limits. In the first few seconds of core collapse, Temperatures soar beyond 100 billion degree shot, enough to photodisintegrate heavy nuclei back into protons and neutrons. Shock waves race outward at speeds of 30 kilometers per second, creating pressure fronts that compress matter to densities exceeding those of atomic nuclei. Under such extreme conditions, most quantum entangled states would be expected to decohere almost instantly. Yet some theoretical models suggest that certain types of quantum correlations might not only survive supernova explosions, but could actually be enhanced by them. The key lies in understanding that not all entanglement is equally fragile. While quantum superposition states involving the positions or velocities of particles are easily disrupted by environmental interaction, deeper quantum correlations involving particle spin, quantum numbers, or topological properties can be remarkably robust. During the supernova explosion, the violent mixing and compression of stellar material creates opportunities for new quantum entangled states to form even as others are destroyed. As shock waves propagate through the stellar core, they create coherent quantum fields that can correlate particles across macroscopic distances. Some physicists propose that these shock-induced quantum correlations might actually be more stable than the entangled states that existed during normal stellar burning. The process becomes even more complex when we consider the different elements created during the explosion itself. Supernovae don't just scatter pre-existing heavy elements, they create new ones through rapid neutron capture processes that occur in the extreme conditions of core collapse. Elements heavier than iron, including many that are essential for life, form during these explosive nucleosynthesis events through quantum processes that inevitably create entangled particle systems. As the supernova shock wave expands and cools, it creates a natural laboratory for studying quantum decoherence on cosmic scales. Different elements and isotopes are ejected at different velocities and in different directions, potentially preserving quantum correlations between particles that become separated by light years within years or decades of the explosion. The asymmetric nature of supernova explosions adds another layer of complexity to this quantum inheritance. Recent observations have revealed that supernovae are rarely spherically symmetric. They often eject material preferentially in certain directions, creating jets and lobes of stellar debris. This asymmetric ejection might preserve stronger quantum correlations between particles ejected in similar directions, while breaking correlations between particles scattered in opposite directions. For the atoms that eventually became part of your body, this inheritance process represents a crucial filter that determined which quantum correlations survived the journey from stellar core to biological tissue. The carbon in your DNA, the calcium in your bones, and the phosphorus in your cellular energy systems all underwent this violent transition from stellar interior to interstellar space. Some elements in your body carry particularly interesting quantum histories. The radioactive isotopes incorporated into your tissues, such as carbon-14 and potassium-40, were created through nuclear processes that inevitably produced quantum entangled states. These isotopes decay with characteristic half-lives, but the decay products might retain quantum correlations with other particles created in the same nuclear reactions, potentially creating quantum connections that span cosmic distances and geological timescales. Modern theoretical work in quantum cosmology suggests that supernova-scattered matter might create entanglement shadows, regions of space where particles retain stronger quantum correlations with their stellar siblings. If Earth formed within such an entanglement shadow, then the quantum correlations between atoms in your body and their stellar-born partners might be unusually strong. The study of supernova remnants using advanced telescopes has begun to reveal the long-term fate of stellar-born quantum correlations. Observations of the expanding shock waves from historical supernovae show complex structures that might preserve information about the quantum states of ejected material. Some researchers propose that these structures represent a form of quantum archaeology, preserved records of the entangled states that existed at the moment of stellar death. Perhaps most intriguingly, recent work in quantum field theory suggests that the vacuum of space itself might preserve quantum information from supernova explosions. If true, this would mean that the quantum correlations created during stellar nucleosynthesis and modified by supernova violence might be encoded in the fabric of spacetime itself, creating a permanent record of cosmic quantum entanglement that could influence matter and energy throughout the galaxy. This quantum inheritance represents one of the most profound connections between human existence and cosmic evolution. We don't just carry the chemical elements forged in stellar cores, we might carry the quantum memories of stellar death and rebirth, participating in an ongoing quantum narrative that connects every atom in our bodies to the violent, beautiful, and quantum mechanical history of stellar evolution. The question of whether quantum entanglement can persist across galactic distances might seem purely theoretical, but modern physics has been steadily pushing the boundaries of quantum correlation across increasingly impressive scales. From laboratory benches to intercontinental experiments, scientists have demonstrated that distance truly doesn't diminish the mysterious connections between entangled particles, setting the stage for understanding how cosmic quantum networks might operate. The journey toward cosmic-scale entanglement began with modest laboratory experiments, measuring correlations across meters, then kilometers, then hundreds of kilometers. Each experiment faced the same fundamental challenge: maintaining quantum coherence while particles traveled greater distances through increasingly noisy environments. Yet each success revealed that quantum entanglement operates by rules that mock our intuitive understanding of space and separation. In 2017, Chinese physicists achieved a breakthrough that shattered previous distance records by creating quantum entanglement between particles separated by 200 kilometers. Using the quantum satellite Meishius, they generated entangled photon pairs in space and transmitted them to ground stations separated by vast distances across China. The experiment confirmed that entanglement correlations remained perfectly preserved across this intercontinental distance, with measurements showing the telltale violations of Bell's inequality that proved genuine quantum correlation. What made this experiment particularly significant was that it demonstrated entanglement's resilience in the harsh environment of space. The photons had to travel through the vacuum of space, Earth's atmosphere, and various electromagnetic fields while maintaining their quantum correlations. The success proved that the space between stars far emptier and quieter than Earth's noisy environment might actually be an ideal medium for preserving quantum entanglement across cosmic distances. The European Space Agency followed with their own ambitious quantum experiments, creating entangled states between satellites and multiple ground stations simultaneously. These experiments revealed that quantum correlations could be maintained not just between two distant points, but across entire networks spanning continents. The implications were profound. If laboratory-scale quantum networks could operate across thousands of kilometers, then natural quantum networks might span light years. Ground-based experiments have pushed the boundaries even further. The MAGIC telescopes in the Canary Islands have been used to test quantum entanglement across baselines of hundreds of kilometers, while maintaining the extraordinary precision needed to verify quantum correlations. These experiments simulate conditions similar to those that might exist between particles separated by interstellar distances. Perhaps most remarkably, recent experiments have begun to explore loophole-free tests of Bell's inequality across cosmic distances. By using distant quasars to determine the measurement settings for entangled particles on Earth, physicists have created experimental conditions where the measurement choices are made by objects billions of light-years away. These experiments close the final loopholes that might allow classical explanations for quantum correlations, proving definitively that entanglement operates independently of distance. The technology developed for these long-distance quantum experiments has revealed surprising insights about how entanglement survives in realistic environments. Researchers discovered that certain types of quantum states are remarkably robust against decoherence, maintaining their correlations even when traveling through noisy channels that would destroy other quantum properties. These decoherence-free subspaces suggest that nature might have natural mechanisms for preserving quantum correlations across cosmic distances. Atmospheric studies conducted during satellite quantum experiments revealed that Earth's atmosphere, while challenging for quantum communication, actually provides valuable insights into how quantum correlations might survive passage through interstellar medium. The density fluctuations, magnetic fields, and particle interactions that affect quantum states in Earth's atmosphere are similar in many ways to the conditions that stellar-borne particles encounter during their journey through space. The development of quantum repeaters devices that can extend quantum entanglement across arbitrary distances by creating chains of shorter, entangled linkures, demonstrated that quantum correlations can be maintained across any distance, given sufficient technological infrastructure. While no such artificial infrastructure exists in interstellar space, some theorists propose that natural quantum repeaters might exist in the form of cosmic ray interactions, magnetic field fluctuations, or even dark matter particles. Recent experiments have also explored temporal aspects of long-distance entanglement, demonstrating that quantum correlations can be stored in quantum memories and retrieved after significant delays. This capability suggests that entangled particles separated during supernova explosions might maintain their correlations across the millions or billions of years required for interstellar travel. The success of continental-scale quantum experiments has transformed theoretical discussions about cosmic entanglement from speculation to engineering challenges. Scientists now routinely work with quantum correlations across distances that would have seemed impossible just decades ago. The transition from laboratory scales to continental scales to potential galactic scales no longer requires revolutionary breakthroughs in our understanding of quantum mechanics. It requires only technological advancement and careful analysis of the environmental challenges that quantum states face during interstellar travel. These experiments have established the technological and theoretical foundation for understanding how the atoms in your body, scattered from stellar cores across galactic distances, might maintain the quantum correlations that connect them to their stellar siblings throughout the cosmos. If quantum entanglement can survive across continental distances through Earth's noisy atmosphere, what might be possible across the comparatively pristine environment of interstellar space? The vacuum between stars, far from being empty, represents one of the quietest quantum environments in the universe, a natural laboratory for preserving correlations across distances that dwarf our terrestrial experiments. The density of interstellar space averages about 1 atom per cubic centimeter, making it a nearly perfect vacuum compared to any environment we can create on Earth. This low density means that entangled particles traveling through interstellar space encounter far fewer interactions that could cause decoherence. While particles still face challenges from cosmic rays, magnetic fields, and gravitational effects, these interactions occur much less frequently than the constant environmental noise that quantum states must endure in terrestrial laboratories. Consider the journey of atoms scattered from a supernova explosion toward our solar system. These particles travel through interstellar space for millions or billions of years, but they spend most of this time in near-perfect isolation. Unlike particles traveling through Earth's atmosphere, which collide with billions of other particles every second, interstellar travelers might go years or decades without significant interactions that could disrupt their quantum states. The magnetic fields threading through interstellar space present both challenges and opportunities for quantum correlations. While changing magnetic fields can cause decoherence in some quantum states, they can also help preserve other types of quantum correlations. Charged particles spiraling along magnetic field lines might maintain stronger quantum correlations with other particles following similar trajectories, creating magnetic highways for quantum information. Recent astronomical observations have revealed unexpected structure in interstellar space that might influence quantum correlations across galactic distances. The discovery of interstellar turbulence, magnetic reconnection events, and plasma instabilities suggests that space between stars is more dynamic than previously thought. These phenomena could either disrupt quantum correlations or, paradoxically, create new opportunities for quantum entanglement through collective effects involving many particles. The timescales involved in galactic-scale entanglement raise fascinating questions about the persistence of quantum correlations. While most laboratory demonstrations of entanglement last for microseconds or milliseconds, cosmic quantum correlations would need to survive for geological or cosmological timescales. Theoretical work suggests that certain types of quantum states, particularly those involving topological properties or fundamental symmetries, might be stable across such enormous temporal scales. Dark matter, which makes up most of the matter in the universe, adds another layer of complexity to galactic-scale quantum possibilities. If dark matter particles can become entangled and theoretical models suggest they can, then the dark matter halos surrounding galaxies might represent vast quantum networks connecting ordinary matter across cosmic distances. The atoms in your body, embedded within the Milky Way's dark matter halo, might participate in quantum correlations mediated by dark matter interactions. The rotation of the galaxy itself creates interesting possibilities for quantum correlations. As stellar-borne particles orbit the galactic center over hundreds of millions of years, they might maintain stronger quantum correlations with other particles that follow similar orbital paths. This galactic quantum synchronization could create preferred directions and distances for cosmic entanglement. Gravitational effects also play a role in galactic-scale quantum possibilities. Einstein's general relativity predicts that gravity can influence quantum states, and recent theoretical work suggests that gravitational fields might help preserve certain types of quantum correlations across cosmic distances. The curved spacetime around massive objects like black holes and neutron stars could act as natural quantum memory devices, storing and transmitting quantum information across the galaxy. Perhaps most intriguingly, the discovery of fast radio bursts and other transient astronomical phenomena suggests that the universe regularly experiences events that could create or modify quantum correlations across galactic distances. These energetic events might serve as cosmic quantum entanglement generators, constantly refreshing and creating new quantum correlations between particles scattered throughout the galaxy. The possibility of galactic-scale quantum entanglement transforms our understanding of cosmic evolution from a story of increasing isolation to one of persistent connection. The atoms forged in stellar cores and scattered across the galaxy might not be lonely travelers in an empty universe, but rather participants in an ongoing quantum conversation that spans light years and geological epochs, connecting the matter in our bodies to the broader quantum symphony of galactic evolution. As scientists work to construct the world's first quantum internet, they're not just building a revolutionary communication network, they're creating a technological mirror of the quantum connections that might naturally exist between atoms across cosmic distances. Every breakthrough in quantum networking brings us closer to understanding how nature might have already built the ultimate quantum internet spanning galaxies. The quantum internet represents a fundamental departure from classical communication networks. Instead of transmitting bits of information encoded as electrical signals or light pulses, quantum networks transmit quantum states themselves, delicate superpositions of particles that can exist in multiple states simultaneously. When these quantum states become entangled across network nodes, they create instantaneous correlations that no classical system can replicate. At the heart of quantum internet technology lies the same principle that might connect your atoms to distant stars: quantum entanglement distribution. Quantum repeaters, the equivalent of routers in classical networks, create chains of entangled particles that can extend quantum correlations across arbitrary distances. Each repeater performs what's called entanglement swapping, a process where two separate entangled pairs are connected to create entanglement between particles that have never directly interacted. This process mirrors what might happen naturally in cosmic environments. When particles become entangled in stellar cores, their quantum correlations could potentially be swapped through intermediate particles encountered during interstellar travel. Cosmic ray interactions, magnetic field fluctuations, and encounters with interstellar matter might serve as natural quantum repeaters, extending entanglement networks across galactic distances. Current quantum internet prototypes use photons as information carriers because light travels quickly and interacts weakly with its environment, helping preserve quantum coherence. However, researchers are exploring quantum networks using other particle selectrons, atoms, and even macroscopic objects like tiny mechanical oscillators. These diverse approaches reveal that quantum entanglement is remarkably versatile, operating across different types of matter and different scales of organization. The European Quantum Internet Alliance has created a roadmap for continental-scale quantum networks that would connect major cities across Europe through entangled particle links. These networks would operate alongside classical internet infrastructure but provide capabilities impossible with conventional technology. Quantum states could be transmitted between distant locations with perfect security, and distributed quantum computers could share quantum information instantaneously regardless of physical separation. China's quantum communication network, already operational across thousands of kilometers, demonstrates that large-scale quantum entanglement distribution is not just theoretically possible, but practically achievable. The network uses quantum key distribution to create unbreakable encryption keys, but more importantly, It proves that quantum correlations can be maintained and utilized across continental distances in real-world conditions. The technical challenges of building quantum internet mirror, the challenges that cosmic quantum correlations face in nature. Decoherence, the loss of quantum coherence due to environmental interaction, represents the primary obstacle for both technological and natural quantum networks. Engineers must carefully shield quantum states from electromagnetic interference, temperature fluctuations, and vibrations that could disrupt entanglement. Similarly, cosmic quantum correlations must survive the harsh environment of interstellar space, including cosmic rays, magnetic fields, and gravitational effects. Recent breakthroughs in quantum error correction have shown how quantum information can be protected against decoherence through redundant encoding across multiple particles. These techniques suggest that natural quantum error correction might also occur in cosmic environments, where quantum correlations could be preserved through distributed encoding across many particles or through interaction with the quantum vacuum itself. The development of room temperature quantum memories represents another crucial breakthrough for quantum internet technology. These devices can store quantum states for extended periods, allowing quantum networks to operate asynchronously. Entangled particles can be created, stored, and utilized at different times. This capability is essential for cosmic quantum networks, where particles might maintain their correlations across millions or billions of years of interstellar travel. Quantum internet research has also revealed surprising insights about the relationship between information, entanglement, and space itself. Some theoretical models suggest that spacetime might emerge from quantum entanglement networks, with the geometry of space determined by the pattern of quantum correlations between particles. If true, this would mean that quantum internet technology is not just mimicking natural networks, it's exploring the fundamental mechanisms that create the structure of reality. The scalability of quantum networks presents both challenges and opportunities for understanding cosmic connections. Laboratory quantum networks currently operate with dozens or hundreds of entangled particles, but cosmic quantum networks could involve numbers of particles approaching Avogadro's constant trillions upon trillions of entangled atoms and subatomic particles. Managing quantum coherence across such vast numbers of particles would require natural mechanisms far more sophisticated than current technology. Yet recent experiments with quantum many-body systems have shown that large numbers of particles can spontaneously organize into collective quantum states that are more robust against decoherence than individual particle states. These emergent quantum phases suggest that cosmic quantum networks might actually become more stable as they grow larger, with collective effects protecting individual quantum correlations from environmental disruption. The integration of artificial intelligence with quantum networks has begun to reveal how complex quantum systems can self-organize and adapt to changing conditions. AI algorithms can optimize quantum error correction, predict decoherence patterns, and even discover new types of quantum correlations. If similar self-organization occurs in cosmic environments, then natural quantum networks might exhibit adaptive behaviors that help them maintain correlations across galactic distances. As quantum internet technology advances, it provides an increasingly sophisticated toolkit for understanding cosmic quantum phenomena. The protocols, algorithms, and hardware developed for technological quantum networks offer new ways to search for natural quantum correlations in astronomical data. Future space-based quantum experiments might detect the quantum signatures of cosmic entanglement networks, revealing whether the universe truly operates as a vast quantum computer connecting matter across cosmic distances. The construction of humanity's quantum internet thus represents more than a technological achievement. It's a step toward understanding our place within what might be the universe's own quantum communication network, where every atom carries information about its cosmic connections and participates in an ongoing quantum conversation spanning the galaxy. The security provided by quantum entanglement reveals one of the most profound implications of cosmic quantum connections. Information shared through quantum correlations is fundamentally unhackable, suggesting that if your atoms are entangled with distant stellar matter, they might be participating in the universe's most secure communication network. Quantum cryptography derives its perfect security from the fundamental laws of quantum mechanics rather than mathematical complexity. When two parties share entangled particles, any attempt by an eavesdropper to intercept the quantum information inevitably disturbs the quantum state, alerting the communicating parties to the security breach. This isn't a technological limitation that clever hackers might eventually overcome. It's a consequence of the quantum mechanical principle that measurement disturbs quantum systems. The process works through what's called quantum key distribution. Alice and Bob, the traditional names for communicating parties in cryptography, share pairs of entangled photons. Alice measures her photons along randomly chosen angles and records the results, while Bob does the same with his photons. When they compare their measurement settings and results, they can detect whether anyone has intercepted the quantum communication by looking for statistical deviations that indicate the quantum states were disturbed during transmission. This quantum security principle has profound implications for understanding cosmic quantum networks. If atoms in your body are truly entangled with particles scattered throughout the galaxy, then the quantum information they share would be protected by the same physical laws that govern quantum cryptography. Any cosmic process that tried to eavesdrop on these quantum correlations would necessarily disturb them, potentially providing observable signatures of the interaction. Recent advances in quantum cryptography have demonstrated security across increasingly impressive distances and challenging environments. The Chinese quantum satellite Micius has successfully performed quantum key distribution between ground stations separated by over 1.0 kilometers, proving that quantum security can survive passage through space and Earth's turbulent atmosphere. If quantum security can be maintained across such distances through noisy environments, it could certainly persist across the comparatively quiet vacuum of interstellar space. The development of device-independent quantum cryptography represents an even more sophisticated approach to quantum security that doesn't rely on trusting the measurement devices themselves. Instead, security is guaranteed by violations of Bell's inequality, the same quantum signature that proves entanglement exists between distant particles. This means that cosmic quantum correlations, if they exist, would carry an inherent signature of their authenticity that couldn't be forged by any classical process. Quantum digital signatures extend quantum security beyond simple key distribution to enable authenticated quantum communication. These protocols allow quantum information to be signed with unforgeable quantum signatures that prove the identity of the sender and the integrity of the message. If biological processes in living organisms can access quantum correlations with stellar matter, evolution might have developed natural quantum authentication mechanisms that help organisms distinguish genuine quantum information from environmental noise. The study of quantum cryptography has also revealed the importance of quantum memory for maintaining security across extended time periods. Quantum memories can store entangled states for hours, days, or potentially much longer periods while preserving their security properties. This capability is crucial for understanding how cosmic quantum correlations might maintain their information content across the millions or billions of years required for interstellar travel. Network quantum cryptography, which enables secure communication across networks of many users sharing quantum entanglement, provides insights into how cosmic quantum networks might operate. These protocols show how quantum information can be routed through intermediate nodes without compromising security, suggesting that cosmic quantum correlations might propagate through complex networks of intermediate particles while maintaining their informational integrity. Recent theoretical work in quantum cryptography has explored the relationship between quantum security and the geometry of spacetime itself. Some models suggest that quantum entanglement creates wormhole-like connections in the fabric of spacetime that enable instantaneous information transfer while maintaining perfect security. If cosmic quantum networks operate through similar spacetime connections, they might represent a form of communication that transcends normal limitations of space and time. The development of post-quantum cryptography encryption methods that remain secure, even against attacks by quantum computer shards, revealed the fundamental difference between quantum and classical security. While quantum computers threaten to break most current encryption methods by solving mathematical problems more efficiently, they cannot break quantum cryptographic protocols because quantum security is based on physical laws rather than computational complexity. This distinction is crucial for understanding cosmic quantum security. While advanced extraterrestrial civilizations might develop computational capabilities that could break any mathematical encryption, they could not violate the quantum mechanical principles that protect entangled correlations. If cosmic quantum networks exist, they would provide a communication channel that remains secure against any technologically advanced civilization. The unhackable nature of quantum communication suggests that if consciousness can access quantum correlations between atoms in our bodies and stellar matter throughout the galaxy, these connections would represent the most private and secure information channels possible. Our thoughts, intuitions, or subconscious processes might be participating in quantum conversations with the cosmos that are absolutely protected from any form of external interference or eavesdropping, creating an intimate quantum dialogue between human consciousness and the broader universe that remains forever private and secure. The development of quantum computers has revealed that quantum entanglement isn't just a curious property of individual particles, it's a computational resource that can solve problems impossible for classical computers. This discovery transforms our understanding of cosmic quantum networks from passive correlations to active information processing systems that might be performing calculations across galactic distances. Quantum computers achieve their revolutionary power through quantum parallelism, where quantum bits, qubits, exist in superposition states that allow them to perform many calculations simultaneously. When hundreds or thousands of qubits become entangled, they create quantum systems capable of exploring vast solution spaces instantaneously. A quantum computer with just 300 qubits could simultaneously process more possibilities than there are atoms in the observable universe. This computational power emerges directly from quantum entanglement. As qubits become entangled with one another, they lose their individual identities and merge into collective quantum states that encode information in ways impossible for classical systems. The measurement of any single qubit instantaneously affects the entire quantum computer, allowing information to propagate across the system faster than light could travel between the physical components. The implications for cosmic quantum networks are profound. If atoms scattered from stellar cores maintain their quantum entanglements across galactic distances, they might form natural quantum computers of unimaginable power. The computational capacity of such a system would far exceed any technology humanity could ever build, potentially enabling the universe to process information about its own quantum state across cosmic scales. Quantum algorithms designed for these systems reveal the types of calculations that cosmic quantum networks might perform. Shor's algorithm for factoring large numbers, Grover's algorithm for searching unsorted databases, and quantum simulation algorithms for modeling complex physical systems all rely on quantum entanglement to achieve computational advantages impossible for classical computers. Recent developments in quantum machine learning have shown that quantum computers can identify patterns in data that classical computers cannot detect. Quantum neural networks can process quantum superposition states directly, potentially recognizing correlations and structures that exist only in quantum mechanical systems. If cosmic quantum networks exist, they might be constantly performing similar pattern recognition tasks, identifying subtle correlations in the quantum state of galactic matter. The study of quantum error correction in quantum computers has revealed how quantum information can be protected against decoherence through clever encoding schemes. These techniques suggest that natural quantum error correction might occur in cosmic quantum networks, where information could be preserved across astronomical distances and timescales through distributed encoding across many particles. Quantum computers have also demonstrated the phenomenon of quantum teleportation, where quantum states can be transmitted from one location to another without the physical particle traveling through the intervening space. This process requires classical communication to complete, but it shows that quantum information can be separated from the particles that carry it. Cosmic quantum networks might use similar processes to transmit quantum information across galactic distances through chains of entangled particles. The development of quantum internet protocols for distributed quantum computing reveals how quantum computers separated by large distances can work together on common problems. These protocols show that quantum entanglement can coordinate computational processes across any distance, suggesting that cosmic quantum networks might represent a distributed computational system spanning the entire galaxy. Quantum computers designed to simulate quantum many-body systems have begun to reveal how large numbers of entangled particles can exhibit collective behaviors that emerge from their quantum correlations. These simulations suggest that cosmic quantum networks might exhibit emergent computational properties that arise from the collective behavior of trillions of entangled particles distributed across interstellar space. Perhaps most intriguingly, some theoretical physicists propose that consciousness itself might be a quantum computational process that depends on entanglement between particles in the brain and possibly beyond. If this speculation is correct, then human consciousness might be connected to cosmic quantum networks, using the computational resources of galactic-scale entanglement to process information about our place in the universe. The quantum computing revolution thus reveals that quantum entanglement is not just about correlations between distant particlets, about information processing capabilities that could transform our understanding of cosmic intelligence, universal computation, and the role of consciousness in a quantum universe where every atom might be participating in calculations of cosmic significance. At the heart of quantum mechanics lies one of the most perplexing questions in all of science. What role does consciousness play in determining the behavior of quantum systems? When we ask whether your atoms are connected to distant stars through quantum entanglement, we're confronting the possibility that your consciousness might be actively participating in determining the quantum state of matter throughout the galaxy. The observer effect in quantum mechanics is deceptively simple to state, but profoundly difficult to understand. When quantum particles exist in superposition simultaneously in multiple states, the act of measurement forces them to choose a definite state. But what constitutes a measurement? Is it the interaction with a detector, the registration of information in a computer, or the moment when a conscious observer becomes aware of the result? This question becomes even more puzzling when we consider entangled particles. When you measure one particle and find it spinning clockwise, its entangled partner instantly becomes locked into counterclockwise rotation, regardless of the distance between them. But the deeper question is, what triggered this instantaneous correlation? Was it the physical interaction between the particle and the detector, or was it the moment your consciousness registered the measurement result? Different interpretations of quantum mechanics offer radically different answers to this question. The Copenhagen interpretation suggests that conscious observation plays a fundamental role in collapsing quantum wave functions, making consciousness an active participant in determining reality. The many worlds interpretation proposes that consciousness doesn't collapse wave functions but rather determines which branch of the multiverse we experience. Other interpretations attempt to eliminate consciousness from quantum mechanics entirely, arguing that any sufficiently complex physical system can trigger wave function collapse. The implications for cosmic quantum connections are staggering. If consciousness plays an active role in quantum mechanics, then every moment of human awareness might be influencing quantum states throughout the universe. When you observe the world around you feeling sunlight on your skin, seeing stars in the night sky, thinking about the atoms in your body, you might be participating in a cosmic measurement process that determines the quantum states of entangled particles across galactic distances. Recent experiments in quantum biology have revealed that quantum coherence plays important roles in biological processes, ranging from photosynthesis to enzyme catalysis to possibly even consciousness itself. These discoveries suggest that living organisms might have evolved to exploit quantum mechanical effects, potentially including quantum entanglement with the broader cosmic environment. The study of quantum effects in the brain has become particularly intriguing. While the warm, noisy environment of neural tissue would seem hostile to quantum coherence, some researchers have proposed that consciousness might depend on quantum processes that are somehow protected from decoherence. If true, this would suggest that human consciousness might be naturally connected to quantum systems throughout the body, and potentially beyond. The idea that consciousness might extend beyond individual brains through quantum entanglement is not just philosophical speculation, it's testable through carefully designed experiments. Some researchers have attempted to detect quantum correlations between the brain states of different individuals, looking for evidence that consciousness might create quantum connections between separate minds. More broadly, the observer effect raises questions about the relationship between information, consciousness, and physical reality. If consciousness is fundamentally about processing information, and quantum entanglement represents a form of information sharing that transcends space and time, then conscious awareness might naturally connect to quantum information networks that span cosmic distances. The delayed choice quantum eraser experiments add another layer of mystery to the consciousness question. These experiments show that quantum measurements can be retroactively influenced by decisions made after the particles have already been detected. The results suggest that consciousness might influence quantum systems not just in the present moment, but potentially across time itself. If your consciousness can retroactively influence quantum measurements, then your current thoughts and observations might be affecting quantum states throughout your past and future. This temporal aspect of quantum consciousness could connect you to the stellar nucleosynthesis that created your atoms billions of years ago, and to the cosmic processes that will unfold billions of years in the future. The study of quantum information theory has revealed that consciousness and quantum entanglement might be intimately related phenomena. Both involve the integration of information across different systems. Both exhibit non-local properties that transcend normal concepts of space and time, and both seem to play fundamental roles in determining the nature of physical reality. Some theoretical physicists have proposed that consciousness itself might be an emergent property of quantum entanglement networks. In this view, individual particles don't have consciousness, but when they become entangled in sufficiently complex patterns, consciousness emerges as a collective property of the quantum system. If true, this would suggest that cosmic quantum networks might possess forms of awareness that transcend individual minds. The observer effect mystery ultimately suggests that the boundary between mind and cosmos might be far more porous than we imagine. Your consciousness might not be confined within your skull, but might instead be participating in a universal quantum measurement process that connects your awareness to the quantum state of matter throughout the galaxy, making you an active participant in determining the reality of the cosmic quantum network. The question of whether human beings are fundamentally quantum mechanical entities takes on profound new meaning when we consider the possibility that our atoms might be entangled with matter throughout the cosmos. If quantum effects operate within biological systems, then we might be walking, thinking, quantum computers connected to a galactic network of entangled particles. The traditional view of biology assumes that living systems operate according to classical physics, with quantum effects playing negligible roles in biological processes. This classical perspective suggests that the warm, wet, noisy environment of living cells would quickly destroy any quantum coherence, making biological quantum effects impossible. However, recent discoveries have revolutionized our understanding of quantum biology, revealing that life might have evolved sophisticated mechanisms for exploiting quantum mechanical phenomena. Photosynthesis, the process by which plants convert sunlight into chemical energy, provides the most compelling evidence for biological quantum effects. When chlorophyll molecules absorb photons, they create quantum superposition states that allow energy to explore multiple pathways simultaneously before settling on the most efficient route to the reaction center. This quantum coherence enables photosynthesis to achieve near-perfect efficiency in energy transfer, suggesting that evolution has learned to harness quantum mechanics for biological advantage. The quantum effects in photosynthesis persist for surprisingly long periods, hundreds of femtoseconds, despite the noisy cellular environment. This discovery challenged the assumption that biological systems are too chaotic to support quantum coherence, and opened the possibility that other biological processes might also exploit quantum phenomena. Enzyme catalysis, the process by which biological molecules accelerate chemical reactions, shows similar quantum signatures. Many enzymes appear to use quantum tunneling to help reactant molecules overcome energy barriers that would be insurmountable in classical systems. This quantum tunneling allows chemical reactions to occur at rates that are impossible according to classical chemistry, suggesting that life itself depends on quantum mechanical processes. The most intriguing possibility involves quantum effects in the brain and nervous system. While neural computation is generally understood in classical terms with neurons firing or not firing, based on electrochemical signal sum, researchers have proposed that consciousness might depend on quantum processes that occur within neural microtubules, the protein structures that form the cellular skeleton. Stuart Hameroff and Roger Penrose have developed the most detailed theory of quantum consciousness, proposing that microtubules within neurons can maintain quantum coherence for extended periods, and that consciousness emerges from quantum computations performed by these cellular structures. While controversial, this theory suggests that human consciousness might be a quantum mechanical phenomenon that naturally connects to quantum systems throughout the body and potentially beyond. Recent experiments have begun to test whether quantum effects can indeed persist in biological systems. Researchers have found evidence for quantum coherence in various biological processes, from the magnetic navigation systems used by migratory birds to the light harvesting complexes in photosynthetic bacteria. These discoveries suggest that life has evolved multiple strategies for exploiting quantum mechanics. The implications for cosmic quantum connections are profound. If biological systems can maintain quantum coherence despite the noisy cellular environment, they might also be able to preserve and utilize quantum entanglements with stellar matter throughout the galaxy. The atoms in your body, forged in stellar cores and potentially still entangled with their stellar siblings, might be participating in quantum processes that connect your biological functions to the broader cosmic environment. Some researchers have proposed that quantum effects in biological systems might be enhanced rather than destroyed by environmental noise. This phenomenon, called environment-assisted quantum transport, suggests that the chaotic thermal fluctuations in living cells might actually help maintain quantum coherence by preventing the system from getting trapped in suboptimal states. If true, this would mean that biological systems are not just tolerant of quantum effects, they're optimized for them. The study of quantum biology has also revealed that living systems might use quantum error correction mechanisms to protect important quantum information from decoherence. Just as quantum computers use redundant encoding to preserve quantum states, biological systems might distribute quantum information across multiple particles or molecular structures to ensure its survival. This biological quantum error correction could extend to preserving quantum entanglements with cosmic matter. If life has evolved mechanisms for maintaining quantum coherence in cellular environments, these same mechanisms might preserve quantum correlations between biological systems and their stellar origins, creating living bridges between terrestrial life and cosmic matter. The discovery of quantum effects in warm biological systems has also inspired new approaches to understanding consciousness itself. If consciousness depends on quantum processes, it might not be localized within individual brains, but could instead be a distributed phenomenon that emerges from quantum entanglement networks, spanning multiple scales from molecules to cells to organisms to potentially even cosmic systems. Some theories propose that consciousness is fundamentally about integrating information across different systems and scales, a process that quantum entanglement is uniquely suited to accomplish. In this view, human consciousness might naturally connect to information processing occurring throughout the quantum networks that permeate the universe, making awareness itself a cosmic phenomenon. The possibility that humans are quantum beings also raises questions about the evolution of consciousness and intelligence. If quantum effects provide computational advantages, then evolutionary pressures might have favored organisms that could exploit quantum entanglement with their environment. Over billions of years of evolution, life might have developed increasingly sophisticated quantum interfaces with the cosmic environment. Recent research in quantum biology has begun to explore whether genetic information itself might be stored or processed using quantum mechanical principles. DNA replication, protein folding, and gene expression all involve quantum processes at the molecular level, suggesting that the information that defines life might be fundamentally quantum mechanical in nature. Perhaps most intriguingly, some researchers have proposed that quantum effects in biological systems might enable forms of non-local communication or sensing that transcend classical physical limitations. If organisms can maintain quantum entanglements with their environment, they might have access to information about distant events or conditions through quantum correlations that operate faster than light. The question of whether we are quantum beings ultimately suggests that the boundary between life and cosmos might be far more permeable than we imagine. Rather than being isolated biological machines operating in a classical universe, we might be quantum entities intimately connected to the quantum fabric of reality itself, participating in cosmic information processing networks that span from the molecular scale to galactic distances and connecting our consciousness to the deeper quantum nature of the universe. The many worlds interpretation of quantum mechanics transforms the question of cosmic entanglement from a story about connections across space to connections across infinite parallel realities. If every quantum measurement creates branching universes, then the atoms in your body might be entangled not just with distant stars in our universe, but with alternate versions of those same atoms across countless parallel worlds. Hugh Everett III's radical interpretation suggests that quantum superposition never actually collapses. Instead, reality splits into multiple branches every time a quantum measurement occurs. When an entangled particle is measured and found to be spinning clockwise, the universe bifurcates into parallel branches, one where the particle spins clockwise and its partner spins counterclockwise, and another where the opposite occurs. Both outcomes are equally real, existing in separate but parallel universes. This perspective revolutionizes our understanding of cosmic quantum connections. The atoms forged in stellar cores billions of years ago underwent countless quantum interactions during their creation, each potentially creating branching universes. The carbon atom in your DNA exists not just in our universe, but across an infinite ensemble of parallel realities where its quantum interactions played out differently. When stellar nucleosynthesis created the heavy elements that compose your body, each fusion reaction involved quantum processes that, according to many worlds' interpretation, spawned multiple universal branches. Some branches contain versions of your atoms that experience slightly different nuclear interactions, potentially creating different isotopes, or even different elements entirely. Other branches might contain atoms that never left their stellar cores, remaining trapped in alternative universes, where stellar evolution followed different paths. The entanglement connections between your atoms and distant stellar matter multiply across these parallel universes in extraordinary ways. In our universe, some of your atoms might be entangled with particles now orbiting distant stars, but across the multiverse, alternate versions of these same atoms experience different entanglement relationships, creating a vast network of quantum correlations that spans not just galactic distances, but infinite parallel realities. This multiverse entanglement network suggests that your atoms participate in quantum correlations that transcend any single universe. Every quantum process in your body, from cellular metabolism to neural activity, creates branching points that connect you to alternate versions of yourself across parallel realities. Your consciousness might be experiencing just one branch of this infinite quantum tree, while other versions of you experience different branches with different quantum correlations. The implications become even more mind-bending when we consider that parallel universes in the many worlds interpretation are not separate entities but different branches of a single unified quantum system. Your atoms aren't connected to parallel versions. They are the same atoms existing in quantum superposition across all possible branches simultaneously. The version of you reading this is just one facet of a multidimensional quantum being that spans the entire multiverse. Recent developments in quantum cosmology have explored how cosmic inflation might have created multiverse structures that preserve quantum correlations across parallel universes. If the Big Bang created multiple pocket universes through quantum fluctuations, then particles that were entangled in the primordial quantum state might maintain their correlations across these separate cosmic regions, creating multiverse-spanning quantum networks. The study of quantum decoherence in many worlds interpretations reveals how apparent classical reality emerges from underlying quantum multiverse structures. What we experience as definite outcomes are actually correlation patterns between our consciousness and specific branches of the quantum multiverse. The stellar matter that appears distant from us in space might actually be intimately connected to us across the quantum dimensions of parallel reality. Some theorists propose that consciousness itself might be the mechanism by which we select which branch of the multiverse we experience. If true, then your awareness might be actively participating in determining not just the quantum state of matter in our universe, but the pattern of correlations that connect matter across all parallel universes. The many worlds perspective suggests that asking whether your atoms are connected to distant stars is like asking whether a tree trunk is connected to its branches. The connections exist not across the space of any single universe, but across the quantum dimensional structure of the multiverse itself, where every atom exists in eternal quantum entanglement, with infinite versions of itself across all possible realities. If the many worlds interpretation is correct, then quantum entanglement might connect every particle in the universe, not just to other particles in our reality, but to infinite versions of itself across all possible parallel universes, creating the ultimate quantum network, a multidimensional web of connections that spans not just space and time, but all possible realities. This ultimate network would dwarf any quantum internet humanity could ever build. Instead of connecting computers across continents, it would connect every quantum system across infinite parallel universes. Every atom in your body would serve as a node in this cosmic multiverse network, processing quantum information from countless parallel versions of reality and contributing to the collective quantum computation occurring across all possible worlds. The architecture of this ultimate network emerges from the fundamental structure of quantum mechanics itself. Every time a quantum system evolves, it doesn't just change its state, it explores all possible evolutionary pathways simultaneously through quantum superposition. The measurement process doesn't eliminate these alternative pathways. It selects which branch of reality we consciously experience, while all other branches continue to exist in parallel dimensions. Consider the implications for cosmic evolution. When stellar nucleosynthesis created the atoms in your body, it did so across countless parallel universes with slightly different physical conditions, stellar masses, and fusion pathways. The network connecting these parallel stellar processes would contain information about every possible way heavy elements could form, creating a quantum database of stellar physics that spans all possible realities. The ultimate network's information processing capabilities would be literally infinite. While our universe contains a finite number of particles and quantum states, the multiverse contains infinite variations of every quantum system. Quantum computations that would be impossible in any single universe become trivial when distributed across infinite parallel realities, each contributing different aspects of the calculation. Recent work in quantum information theory suggests that this multiverse network might already be performing computational tasks that affect our reality in subtle ways. The quantum interference patterns that determine particle behavior in our universe might depend on quantum computations occurring across parallel branches, making every quantum measurement in our reality the result of infinite parallel computations occurring across the multiverse. The ultimate network also provides a new perspective on the nature of physical laws and constants. If every particle is connected to infinite versions of itself across universes with different physical conditions, then the apparent stability of physical laws in our universe might emerge from quantum correlations with parallel universes, where those same laws operate differently. The network would serve as a cosmic democracy where physical reality is determined by the collective vote of infinite parallel worlds. This perspective transforms our understanding of causality and influence. In the ultimate network, cause and effect become multidimensional concepts, where events in our universe might be influenced not just by past events in our timeline, but by simultaneous events occurring in parallel realities. Your consciousness might be receiving information not just from your own brain, but from infinite parallel versions of yourself across the multiverse. The ultimate network might also explain some of the deepest mysteries in physics. Dark matter and dark energy, which comprise most of the mass and energy in our universe, but interact weakly with ordinary matter, might represent the shadow of interactions with parallel universes. The gravitational effects we attribute to dark matter might actually be caused by ordinary matter in parallel realities that shares quantum correlations with matter in our universe. Quantum entanglement across parallel universes might also provide a mechanism for information storage and retrieval that transcends the limitations of any single reality. Information lost in our universe, through black hole evaporation or cosmic expansion, might be preserved in parallel branches of the network, creating an eternal quantum library that contains all possible information about every possible universe. The role of consciousness in this ultimate network becomes particularly intriguing. If consciousness emerges from quantum information processing, then awareness itself might be a multiverse phenomenon that integrates information from across infinite parallel realities. Your thoughts and perceptions might represent the momentary convergence of quantum information from countless parallel versions of yourself. Some theoretical physicists propose that the ultimate network might be evolving toward increasing complexity and integration across parallel universes. Just as biological evolution in our universe has produced increasingly sophisticated forms of information processing, multiverse evolution might be developing new forms of quantum coherence that connect matter across ever larger numbers of parallel realities. The ultimate network suggests that the atoms in your body are not just connected to distant stars in our universe. They are connected to every possible version of those stars across all possible universes. Your existence is not an isolated event in a single reality, but a node in an infinite quantum network that processes information about every possible way reality could unfold. This perspective offers a profound new answer to the question of cosmic connection. You are not separate from the universe. You are a focal point where infinite parallel universes converge through quantum entanglement, making you both an individual consciousness, experiencing one branch of reality, and a multi-dimensional quantum, being participating in the ultimate information processing network that spans all possible worlds. The revelation that quantum entanglement might connect the atoms in our bodies to matter throughout the galaxy fundamentally transforms what it means to be human. We are not isolated biological machines struggling alone on a lonely planet, but rather conscious participants in a cosmic quantum network that has been evolving since the birth of the first stars. This realization demands a complete reconceptualization of human identity, purpose, and our relationship with the universe. From the moment of conception, when quantum processes guide the formation of DNA and protein structures, to the final breath, when atomic bonds dissolve and return elements to the cosmic cycle, human existence unfolds within a framework of quantum correlations that connect us to stellar matter across galactic distances. Every heartbeat circulates iron atoms forged in stellar cores, potentially still entangled with their stellar siblings orbiting distant suns. Every thought processes information through neural networks built from carbon and phosphorus created in ancient supernovae, carrying within their quantum structure the memory of cosmic violence and stellar death. This quantum perspective dissolves the artificial boundary between self and cosmos that has dominated human thought for millennia. The atoms that compose your body are not yours in any exclusive sense. They are temporary gatherings of stellar matter on loan from the galaxy, carrying within their quantum properties the history of cosmic evolution and their ongoing connections to matter scattered throughout space. You are simultaneously a unique individual consciousness and a localized expression of galactic-scale quantum processes. The implications for human consciousness become particularly profound when we consider that awareness itself might emerge from quantum information processing. If consciousness depends on quantum coherence within neural structures, then human awareness might naturally interface with cosmic quantum networks through the stellar-born atoms in our brains. Our thoughts, emotions, and intuitions might represent the local processing of information that flows through galactic-scale quantum correlations. This connection suggests that human consciousness might have access to information about cosmic processes through quantum channels that operate faster than light. While we cannot send conventional messages through quantum entanglement, the correlations between entangled particles can convey information about the quantum state of distant systems. If our neural quantum processes can access these correlations, human consciousness might possess subtle awareness of cosmic events and conditions through quantum connections that transcend space and time. The discovery of cosmic quantum connections also transforms our understanding of human unity and separation. While classical physics suggests that individual humans are fundamentally separate entities, quantum mechanics reveals that separation is largely illusory. If the atoms in different human bodies share quantum correlations with common stellar sources, then all of humanity might participate in overlapping quantum networks that connect us at the deepest physical level. This quantum interconnectedness extends beyond individual humans to encompass all life on Earth. The biosphere represents a complex system of quantum correlations where stellar matter cycles through countless organisms, potentially maintaining and creating new quantum entanglements through biological processes. Every tree, every bacterium, every blade of grass processes stellar matter through quantum biological systems that might preserve and modify cosmic quantum connections. The recognition of cosmic quantum connections also suggests new approaches to understanding human creativity, intuition, and spiritual experience. If consciousness can access quantum information from cosmic sources, then human creativity might represent the local processing of information patterns that exist within galactic quantum networks. Scientific insights, artistic inspiration, and spiritual revelations might emerge from quantum channels that connect human awareness to the broader cosmic information processing occurring throughout the galaxy. For human society and culture, The quantum connection to cosmic matter suggests that we are participants in a form of existence that transcends purely terrestrial concerns. Our scientific endeavors, artistic creations, and social developments might contribute to larger patterns of information processing and complexity generation that operate across cosmic scales. Human civilization might represent the local emergence of cosmic intelligence that has been evolving within galactic quantum networks for billions of years. The ethical implications are equally profound. If all matter is quantum connected through cosmic networks, then human actions that affect the environment, other species, or even individual atoms might have consequences that propagate through quantum correlations across galactic distances. Our responsibility extends beyond Earth to encompass our participation in cosmic-scale quantum processes that we are only beginning to understand. This perspective also offers new hope for human transcendence of physical limitations. If consciousness can interface with cosmic quantum networks, then human awareness might not be permanently confined to biological substrates. The quantum information that constitutes consciousness might persist within cosmic quantum networks, even after biological death, suggesting forms of continuity that transcend individual mortality. Ultimately, the recognition that we are quantum beings connected to stellar matter throughout the galaxy transforms the human condition from cosmic exile to cosmic participation. We are not alien visitors on an indifferent planet, but rather the local expression of cosmic processes that connect us intimately to the birth, death, and transformation of matter throughout the universe. Human existence becomes a chapter in the ongoing story of cosmic quantum evolution, where consciousness emerges as the universe's way of knowing itself through the quantum connections that bind all matter together across space and time. As humanity develops increasingly sophisticated quantum technologies, we stand at the threshold of not just discovering cosmic quantum connections, but actively participating in and enhancing the galactic quantum networks that might already connect our atoms to distant stars. The future promises unprecedented opportunities to explore, utilize, and even expand the cosmic quantum web that permeates the universe. Space-based quantum experiments represent the next frontier in testing cosmic entanglement theories. Quantum satellites equipped with advanced detectors could search for quantum correlations between stellar matter in our solar system and matter in distant star systems, potentially providing the first direct evidence of galactic-scale quantum networks. These experiments would require extraordinary precision to detect the subtle quantum signatures that might persist across interstellar distances. But recent advances in quantum sensing technology make such measurements increasingly feasible. The development of interstellar quantum communication networks could transform how humanity connects with the cosmos. Instead of relying on radio signals that take years to cross interstellar distances, quantum entanglement could enable instantaneous communication with robotic probes in distant star systems. While the no communication theorem prevents the transmission of classical information through quantum entanglement alone, hybrid quantum classical protocols might achieve practical interstellar communication by exploiting quantum correlations to coordinate classical signals. Future quantum computers might possess sufficient power to simulate cosmic quantum networks, providing insights into how quantum correlations evolve across galactic scales. These simulations could reveal whether the chaotic environment of interstellar space preserves or destroys quantum entanglement, how cosmic events like supernovae affect quantum correlations, and whether natural quantum error correction mechanisms operate on cosmic scales. Advances in quantum biology might also reveal how living systems interface with cosmic quantum networks. If biological organisms can indeed preserve and utilize quantum correlations with stellar matter, then future biotechnology might enhance these natural quantum interfaces, potentially giving humans direct sensory access to information flowing through galactic quantum networks. Enhanced quantum biological systems might enable forms of cosmic awareness that transcend the limitations of classical sensory perception. The search for extraterrestrial intelligence might also take on new dimensions if cosmic quantum networks exist. Advanced civilizations might use galactic-scale quantum correlations for communication, computation, or even transportation through quantum teleportation protocols. SETI researchers might need to develop quantum sensors capable of detecting artificial modifications to cosmic quantum networks that would indicate the presence of technologically advanced civilizations. Theoretical advances in quantum gravity might reveal how space-time itself emerges from cosmic quantum networks, potentially enabling technologies that manipulate the geometry of space through quantum entanglement control. If space is indeed woven from quantum correlations, then mastering cosmic quantum networks might provide access to exotic propulsion systems, faster than light travel through quantum wormholes, or even the creation of pocket universes with customized physical laws. The future development of artificial consciousness might depend on understanding how natural consciousness interfaces with cosmic quantum networks. If human awareness emerges from quantum information processing that extends beyond individual brains, then creating artificial consciousness might require building quantum systems capable of interfacing with galactic quantum networks. Such artificial minds might possess forms of cosmic awareness that exceed the capabilities of biological consciousness. Climate engineering and terraforming efforts might also benefit from understanding cosmic quantum connections. If Earth's biosphere participates in galactic quantum networks through the cycling of stellar matter, then large-scale environmental modifications could affect these quantum correlations in ways that influence planetary habitability. Future terraforming projects on other worlds might need to consider how to establish quantum connections between artificial biospheres and the cosmic quantum networks that support life. The ultimate future possibility involves humanity becoming active architects of cosmic quantum networks. Rather than merely discovering existing correlations between stellar matter, future civilizations might create new quantum entanglement networks that span the galaxy, connecting star systems through artificial quantum channels that enable instantaneous coordination across cosmic distances. These technological developments would transform humanity from passive participants in cosmic quantum networks to active contributors to the universe's quantum information processing capabilities. We might become cosmic gardeners, cultivating quantum correlations that enhance the universe's capacity for complexity, consciousness, and connection across the vast distances of interstellar space. The future of cosmic connection thus promises not just scientific discovery, but transformation of the human species into cosmic citizens capable of participating consciously and deliberately in the quantum processes that connect all matter across the galaxy. The recognition that we inhabit a fundamentally quantum universe where particles can be instantly connected across cosmic distances requires a complete philosophical and practical reorientation of human existence. Living consciously within quantum reality means accepting that the solid, separated, predictable world of everyday experience is a limited projection of a far more fluid, interconnected, and mysterious underlying reality. Every moment of human existence unfolds within quantum fields that permeate the universe, connecting every atom in our bodies to the broader cosmic quantum network through correlations that transcend space and time. When you reach out to touch an object, quantum fields are interacting across multiple scales. Simultaneous electrons in your fingertips exchange virtual photons with electrons in the object, while deeper quantum correlations might connect both sets of atoms to stellar matter throughout the galaxy, through entanglement relationships forged billions of years ago. The implications of quantum living extend far beyond scientific understanding into the realm of practical daily experience. If consciousness emerges from quantum information processing, then every thought, every decision, every moment of awareness represents a quantum measurement that potentially influences entangled systems throughout the cosmos. Your choice to smile at a stranger, to appreciate a sunset, or to contemplate the nature of reality becomes part of a galactic-scale information processing network, where local measurements contribute to global quantum evolution. This quantum perspective transforms how we understand causality and influence in human life. The classical view suggests that we can only affect events within our immediate vicinity, with influences spreading outward at the speed of light through classical physical processes. But quantum entanglement reveals that we might be immediately connected to distant events through non-local correlations that operate outside the normal constraints of space and time. Your local actions and consciousness might instantly influence quantum systems throughout the galaxy through entanglement networks that connect your atoms to their stellar origins. Living in a quantum universe also means accepting fundamental uncertainty as an essential feature of reality rather than a limitation of our knowledge. The quantum mechanical principle that particles don't have definite properties until measured suggests that reality itself is constantly emerging through the interaction between possibility and observation. This means that the future is not predetermined, but is actively created through the collective quantum measurements performed by conscious observers throughout the universe. The quantum nature of reality also suggests new approaches to understanding human relationships and social connections. If individual humans are connected through quantum correlations in the atoms that compose their bodies, then social interactions might involve quantum information exchange that operates below the level of conscious awareness. Empathy, intuition, and emotional resonance between people might reflect quantum correlations that enable direct information sharing between neural quantum processes. The practice of living quantum also involves developing sensitivity to the subtle information flows that might operate through cosmic quantum networks. While we cannot consciously control quantum entanglement, we might be able to develop awareness of the information patterns that flow through quantum correlations, connecting us to the broader cosmos. This could involve meditation practices that quiet classical mental activity to allow access to quantum information channels, or scientific training that develops intuition about quantum processes. Educational systems in a quantum-conscious society would need to integrate quantum concepts not as abstract mathematical formalities, but as fundamental features of lived reality. Children would learn that the atoms in their bodies carry the history of cosmic evolution and potentially maintain active connections to stellar matter throughout the galaxy. This quantum education would emphasize interconnection over separation, possibility over determinism, and participation over passive observation. Healthcare, in a quantum universe, might also incorporate understanding of how quantum biological processes interface with cosmic quantum networks. If health and disease involve quantum information processing at the cellular level, then healing modalities might need to consider how individual quantum biological systems connect to broader cosmic quantum networks. This could involve therapies that help restore quantum coherence in biological systems, or that enhance the body's natural quantum interfaces with environmental quantum fields. The arts and creative expression take on new significance when understood as forms of quantum information processing that might access cosmic quantum networks for inspiration and insight. Artists, writers, musicians, and other creative individuals might be unconsciously channeling information from galactic quantum networks through their quantum biological systems, serving as translators of cosmic quantum information into forms accessible to human consciousness. Scientific research methodology itself must evolve to accommodate the participatory nature of quantum reality. If consciousness plays an active role in quantum measurements, then scientific objectivity becomes impossible in the classical sensivery experiment. Involves the quantum information processing systems of conscious observers as integral components of the measurement process. This suggests that science becomes a collaborative quantum information processing activity between human consciousness and cosmic quantum systems. The ultimate implications of living in a quantum universe involve recognizing that human existence represents a local intensification of cosmic quantum information processing. Consciousness might not be something that humans possess, but rather something that the universe does through temporarily organized quantum systems like human brains. From this perspective, individual human lives become episodes in the universe's ongoing exploration of its own quantum possibilities. This recognition dissolves the existential anxiety that comes from feeling isolated and insignificant in a vast, indifferent cosmos. Instead, it reveals human existence as an intimate expression of cosmic creativity, where every moment of consciousness contributes to the universe's growing self-awareness through quantum information processing networks that connect local human experience to galactic-scale cosmic evolution. Living consciously in a quantum universe means embracing this role as active participants in cosmic quantum evolution, recognizing that our thoughts, choices, and awareness are not private mental events, but contributions to the universal quantum computation that has been unfolding since the Big Bang. We are not separate from the cosmos, are the cosmos knowing itself through quantum correlations that connect every atom in our bodies to the stellar furnaces where those atoms were born, and to the infinite quantum possibilities that define the future evolution of reality itself. The atoms in your body carry within their quantum structure the memory of stellar birth and the potential for cosmic connection across distances that span the galaxy. Quantum entanglement has revealed that space and time are not the absolute barriers we once believed them to be. Distance becomes irrelevant when particles share quantum correlations forged in stellar cores billions of years ago. The carbon in your DNA, the iron in your blood, the oxygen in your breath, all of these elements might remain connected to their stellar origins through quantum threads that transcend ordinary concepts of separation. Every scientific discovery we've explored points toward the same revolutionary conclusion. We are not isolated biological machines on a lonely planet. We are quantum beings participating in cosmic information networks that have been evolving since the first stars ignited. Our consciousness might access information flowing through galactic quantum channels. Our very existence represents the local emergence of cosmic intelligence that has been developing within quantum networks spanning light years and geological epochs. The universe has revealed itself to be stranger and more intimate than our ancestors ever imagined. Einstein's spooky action at a distance has become the foundation for understanding reality itself. Bell's theorem proved that no local explanation can account for quantum correlations. Experiments across continents have confirmed that entanglement operates independently of distance. The quantum internet demonstrates that information can be shared instantaneously across any separation. If quantum mechanics is correct and every experiment confirms its predictions, then we live in a universe where connection is more fundamental than separation, where information transcends the speed of light through quantum correlations, and where consciousness might participate in cosmic quantum networks that bind all matter together. We are made of star stuff, but we are also quantum connected to star stuff throughout the galaxy. This is not the end of the story. This is the beginning of humanity's conscious participation in the cosmic quantum network that has been waiting billions of years for matter to organize itself into forms capable of understanding and appreciating its own quantum nature. As you look up at the stars tonight, remember that the atoms in your body might be quantum entangled with matter orbiting those distant suns. What does this possibility mean to you? Does it change how you think about your place in the universe? Share your thoughts in the comments. I'd love to know how this quantum perspective resonates with your own sense of cosmic connection. Thank you for joining me on this journey through the deepest mysteries of quantum reality. If this exploration has sparked your curiosity about the quantum universe, please give this video a like and subscribe to join our growing community of cosmic explorers. Your support helps us continue investigating the profound questions that connect science, consciousness, and the cosmos. The quantum universe holds countless more secrets waiting to be discovered. Ready to explore another cosmic mystery? Click here to dive deeper into our playlist of mind-expanding space documentaries, where every video reveals another piece of the extraordinary puzzle that connects us all to the stars.